Okay, here we go. We're going to go ahead and go to Moodle Mobile again. This time we're talking about the conservation of energy. So, of course, I need to do the theory, but let's just look at some of the things that we'll need to download while that is taking place. All right. So I have lecture notes here. I'll probably replace those, but for right now, let's just go ahead and pull down our 13 conservation of energy experiment for video physics. I'll pull that down, and of course, I'll pull down the calculator as well. So what is conservation of energy? The conservation of energy is a statement, and it basically says that energy is neither created or destroyed, only transformed. Okay, so let me just get out of this and let's go to paper, 553. And this will probably need to refresh. So let's create a new space. And even though we're going to be talking about the conservation of energy, you know what? I'll just make this the conservation of energy. I'll just call that this. Conservation of energy. All right. So we start off with the idea of work. And work is the net force times the displacement. And I'm just going to say, let's just call this force in the x direction, and let's say our displacement is in the x direction as well. Remember that this is just a Newton times a meter, and this is identical to a joule. A joule is our unit for energy. There are going to be two kinds of energy that we're going to use as well. And then I want to relate work to energy. So kinetic energy, that's moving energy. And I'm just going to call that KE, is 1/2 times the mass of the object that's moving times its velocity squared. And we're going to also have PE. This is going to be gravitational potential energy. And it is the mass of an object times the gravitational pull near the surface of the Earth times the height of this object. And that's how high it is from the center of the Earth. In our case, it's really, we can say it's how high it is from the center of Earth. Yes, that's correct. That would be correct. So instead of writing all of this out, we just typically write KE is equal to 1/2 mass times velocity squared, and PE, which is a gravitational potential energy, is mgy. Okay. Now there's a relationship between these two energies, and I mean, well, not only two energies, but work and energy. So we say that the work is equal to, or the change in work is equal to the change in kinetic energy plus the change in potential energy, gravitational potential energy. All right. And so what do we do here? We know what those deltas actually represent. We know that this is the work in the final scenario minus the work in the initial scenario is equal to the kinetic energy final minus kinetic energy initial plus potential energy final minus potential energy initial. So we'll end up substituting what we need to substitute in here. But we want to get to the conservation of energy from this particular theorem.